Now to oxidation. Aldehydes are oxidized to carboxylic acids by potassium permanganate in the presence of a base, potassium dichromate, and silveramine, also known as Tollens reagent. Here I use silveramine. If you react it with an aldehyde in water, you will produce a carboxylate and solid silver, which will form a silver mirror in your glassware. This carboxylate can be protonated further to form the carboxylic acid. In general, ketones are resistant to oxidation by the above reagents. Potassium permanganate, potassium dichromate, and silveramine will not react to ketones. However, we should take note that there are exceptions to this. One interesting oxidation method is called Baeyer-Villiger oxidation. This is an insertion of an oxygen atom adjacent to a ketone or aldehyde carbonyl. How does this work? I've shown here a cyclic ketone reacting with a peroxy acid. An example of a peroxy acid is MCPBA. The lone pairs of the oxygen can attack the carbonyl carbon to form this compound after proton exchange. Electrons in this bond here can reform the double bond. If this bond is reformed, carbon will have an excess of electrons. To allow the formation of this double bond, either this bond or this bond will break and a new bond to this oxygen will form. This is a migration. The migratory aptitude has been already studied and it follows this pattern. These groups are easy to migrate while the groups here are less likely to migrate. As you see here, if we don't consider this bond, this is a secondary alkyl group. If we don't consider this bond, this is a primary alkyl group. In this sequence, a secondary alkyl group has a higher migratory aptitude, so this bond will likely break, and a new bond will form with oxygen here, which is the case. Once the bond forms, this bond will break and you will form the carboxylic acid plus a cyclic structure in which an oxygen is inserted. We start here from a 5-membered ring. The end product is a 6-membered ring. This is a ketone and this is a cyclic ester. Another example is with acetophenone here. If you react it with MCPBA, an oxygen may be inserted at this position or at this position. And if you consult this order of migratory aptitude here, phenyl is more likely to migrate compared to methyl. So, the oxygen will be inserted at this location to give you this product. Aldehydes and ketones can be reduced by these sets of reagents. The end result will be an alcohol. The double bond will just be reduced to give you this alcohol. If this is an aldehyde, you will get a primary alcohol. If it's a ketone, a secondary alcohol will be produced. Any CC double bond in the molecule will also be hydrogenated if you use metal catalyzed hydrogenation. If you want the CC double bond to be retained, you should use sodium borohydride or lithium aluminum hydride in your reduction. For example, this compound here, an alpha-beta unsaturated carbonyl compound, reaction with sodium borohydride and acid workup will give you this compound. The carbonyl group is reduced, but the CC double bond remain unscathed. Aldehydes and ketones can also be reduced directly to the alkanes. One such method is called Clemmensen reduction. It uses zinc amalgam in about 40% aqueous HCl, and you need to heat it up. An alternative to this is to use zinc powder in a dry solvent with HCl. In this case, if you use Clemmensen reduction, you will convert your carbonyl group into a methylene group, the oxygen will be removed completely. It does not reduce carboxylic acids, esters, and amides. One interesting use of this method is the preparation of unbranched alkyl benzene through phenyl ketones while avoiding rearrangement. As I have discussed in the topic of aromatic hydrocarbons, Friedel-Crafts alkylation is prone to rearrangement. For example, the formation of propylbenzene is not very effective if you use 1-propyl chloride and aluminum chloride. You will produce an isopropyl benzene in that case. A workaround for that synthesis is the Clemmensen reduction. What is needed is to first prepare a phenyl ketone. You can do Friedel-Crafts acylation first. You can use, for example, here a propanoyl chloride in the presence of aluminum chloride. You can do acylation. And then you can use Clemmensen reduction to remove this carbonyl group, and you will produce a propylbenzene. Clemmensen reduction uses a strong acid, and this condition may be inappropriate if you have acid-sensitive functionalities. An alternative to Clemmensen reduction is to use Wolff-Kishner reduction. This condition is basic. You will use hydrazine with a base and heat, and the result will be the same. Another method that is applicable to aryl ketones is the use of palladium catalyzed hydrogenation in ethanol. You can also convert your phenyl ketones to alkyl benzenes.